Okay, class. Some announcement here. All right. For the midterm, right, it's going to be tentatively next Monday. All right. I will double confirm by this Thursday. And this again, tentative lah. Okay. I would like to make this midterm fully online. Okay, for the sake of safety, as we can see that, yeah, more than 20K per day. All right. So now, what is the catch? Okay, of for you all to do online? Okay, 115 students. Now the catch is that the questions will be simulating based. Okay, simulating based plus like normal calculation. So normal calculation means that, our normal midterm, you get a piece of paper, you write, right? Calculation, and tell some stories. So I actually make this question, all right, 60% or around 70% is simulating based. 30% is a calculation based. Okay. And then, so what you all need to do is basically, I will tell you what to model. If you have followed my class, every time I ask you to model, you will laugh. You just load, open, talk, submit, finish. If you never try in my class, you may struggle. Okay, you may struggle. Like I said, the best way is that make good use of this time, right, to practice. Okay, so your answer, okay, of course, for those written one, you need to write lah, and then take snapshot. Okay, save in a PDF. For simulating one, it's basically screen capture your result. Screen capture your model, screen capture your setting, screen capture your result, screen capture your scope, whatever. So you think that you may need to show me. Okay. Then let me warn you again. I don't believe in coincidentally two of the drawing are exactly the same. Don't tell me that. If this does happen, right? You go and buy Magnum. Close eye 1, 2, 3, 4. Tomorrow first prize. All right. So this is the catch. Okay. So the chapter cover will be the power electronic device and whatever we end at this coming Thursday for the DC to AC converter. Okay. So that is basically, yeah, how we are going to conduct the midterm. Like I said, if you don't know simulating, you know how to answer my question, you still get some marks. You won't get 0. Okay. So plus a little bit of practice on the simulating, right? You should be able to answer my question easily, I would say. Okay. Because I'm not going to come out something that I never mentioned or taught in the class. So everything, okay, is inside my slide. And of course, read my question carefully. Because I usually like to make everybody answer different. For example, I will ask you to set a certain value based on your student ID last number, for example. Then you copy for your friend will get wrong because unless your friend coincidentally, the last 2 number is exactly, that's what I believe. Because I look at the number, right, there are a few, really the last 2 number is the same. They want no worry, they want I'll trust you. But if you show me the two drawing is exactly the same story lah. Okay, so all right, I won't give straight 0 because there must be one person who do the thing, right? The other copy. So I will just divide it by 2. If I found 4 person, I divided by 4 lah. So you think like 20 mark, right? Maximum 20%, you got 1 mark lor. Okay, so that is the basic idea of this coming, what we call this midterm. Now, why I cannot confirm the midterm is now because from this year onward, our internal midterm test assignment need to go through a moderation process. So yeah, I may need longer time to do that, okay? But of course, I will try to get it done by this Thursday so I can confirm with you. So Monday, you all no need to come on next Monday, right? Sit at home, comfortably answer my question. All right? Okay, so any questions? I prefer handwriting. I prefer handwriting. Because you already can cut and paste your result for your friend already for the Simulink. Right? So please, handwriting lah. Okay? Yeah. Oh, you mean this type of pen? This type accept. Because it show your writing, your style, your writing. Okay, can, no problem. This one can. You can use a computer pen. Those can write one. Because my point is that one is really difficult for me to catch who's copy whose. You use Microsoft Word, Area, the same font, you cut and paste the same result. It's a bit difficult. So writing is the best. Okay, so let us just continue on our lecture. Is actually we are quite lag behind. Okay, we talk about modulation. Okay, this is again very important one. And then we talk about modulation without any filter, and it does work for variable speed drive or variable frequency drive. Okay, now I missed one thing here. Okay, now this is one of the example of the inverter without filter, right? It used in variable frequency drive or variable speed drive. Another application, okay, which is actually quite common in the past decade is, I believe you heard that there is a inverter aircon, right? Okay, in the old day we don't have this, but now we have. So it's the same concept. Inside this inverter aircon, right? The compressor. Now the compressor, if 1 horsepower, is around 760 something watt. Okay. Now with a normal non-inverter, the motor is either on or off. Okay. So when the motor on, it have a very large inrush current. Okay. And when it stop, right, it off and on and off again. So it's actually very consuming power. Because even though your temperature or your fan set at 1, but the compressor is running at full speed. So now they add what we call inverter. They don't call it variable frequency drive, but in fact you look at it's a drive anyway. But this name is not wrong because you look at the topologies, it's still inverter, right? So with that inverter, right, this what we call compressor motor, right, will not stop running. Okay, it will slow down the speed or increase the speed, okay, as it needed. So it does not have any inrush. It's just like what we show the balloon example, okay, easily can give you at least 30% and above power saving. That's why it's expensive, because literally you buy one inverter put inside, right? The what we call non-inverter one, a normal one around like 800 ringgit, right? But the inverter is more than 1,000. So that extra money is actually you are buying this thing, put inside the compressor, that's all. Okay, but for the long run, right? You see, a lot of people will say, wow, 300 ringgit expensive leh, 800 suddenly become like 1,002. But imagine, if every month it helps you to save 50 ringgit, 6 months you get back the money already, right? 6 months it give back the money, and the rest of the 2-3 years is the money you really save. Okay, so these are what we call long-term plan. Okay, for any consultant, you need to learn. Okay. All right, so this one I just add on so that because this nowadays I see there are quite a lot of inverter aircon. Usually those branded like Panasonic, Daikin, and so forth Okay, now we continue. Okay, I show how this can be modeled in Simulink. Okay, and later we talk about designing a filters so that we can produce the sine wave voltage and sine wave current output. Then after that, okay, these are the transfer function. Okay, and then we implement a simple filters, and we manage to convert, okay, those SPWM into a sine wave, all right, with a very, very low THD. And now we move further on to feedback control, because we need to maintain the voltage, right, at certain level. So these are the feedback control, okay, for the inverter. Okay, these are important block diagram, Okay, in exam, I will ask you to draw the block diagram of a feedback control. So this is something you should draw, and then write down their equations. Okay, and then we move on. Okay, this is what we done last week. Okay, for the feedback control. All right. So I believe last week we have some students showing the waveform a little bit weird, right? Okay, most of them are because they didn't set the PI correctly. Okay, they didn't set, that's why it's not settling. So anyways, okay, you can, all your LC filter are wrongly calculated, or your switching frequency is wrong, because these are all interrelated. One wrong, everything wrong. All right. And then if everything is correct, you should have exactly 230 watt as set by your what we call this your reference, and then you will have a very, very low, okay, THD. All right. So this topology on this side is actually widely used in many of these stand-alone inverter. Means the inverter are not connected to the grid. Okay, it's stand-alone, like the inverter that used inside your car or camper car, anything like not grid connected, okay, system. Now, you may have a question about how to get 400 watt here. So for the real inverter, right? This is the real inverter, okay? How it works is that, okay, you have a battery input, and the battery is actually 12 watt, 24 watt, or 48 watt. All right. So these are the real inverter, right? Your car is 12 watt, right? Your bus is 24 watt, right? Or the off-grid, usually they add up to 48 watt. So how it works is that you can see, in fact, there are 3 stages here. Okay, the first stage is that, okay, let's say it's 24 watt. It goes to a DC to AC converter. And it's a high frequency push-pull. Remember our very first DC AC is a push-pull, right? Okay, so it used a transformer to step up this to around 400 watt. But AC. But this AC is not sine wave, remember? The push-pull, it will give you a square wave, right? It will give you a square wave. And then after that, it go through again a AC to DC converter. convert back to DC. Okay, with a capacitor, you actually flatten this, right? So the output of this at this point here, you will get a DC, but 400 watt. And of course, the rest is what we have studied, is a full bridge inverter with a filter. So the output here, you will have a sine wave. So this is how a commercial inverter works. In fact, I have one of these. Okay, that's why I know. All right, because I open it up, this is how it looks like. You see, this one is the transformer. This is high frequency transformer. Okay, that's mean the push-pull is not using a 50 Hz transformer. Remember I say 50 Hz transformer are heavy, big, but they use high frequency. Okay, 10 kilohertz, 20 kilohertz. So when the frequency increases, the transformer size becomes smaller. Same like inductor. Your frequency increase, your inductor size become smaller. Okay, so and there is another one, this one. This is the inductor. This is the LC filter, the inductor. So big. Okay, this is the inductor. All right. So you can see this is the DC input. This is the DC input. It comes in here first. Okay, and then of course this will be the output lah. And then it connect, okay, to the 3-pin output. So this is one of the way to design inverter that does not use big transformer, does not use heavy transformer. The limitation is that the max you can go is around 5 kilowatt. Okay, the one that you see here is around only 2 kilowatt. Okay, and then another example. This example you can see. This is not the LC filter. The LC filter is here. The LC filter is here. Now this is the output transformer. Okay. Now the output transformer made in the way that they don't have these 2 stages. They actually take these 2 stages out. Okay. No more. No this stage. Straight away apply battery to the DC to AC. 34 watt, for example. Then your output also 34 watt, right? So they put a transformer here, the big transformer. Okay, they put a transformer at the end here, where your 24 watt output AC is here after the filter. Then you will have 230 watt. That's why you can see the transformer size is very much bigger compared to the high frequency one. So there are both types of design. Okay. I won't say which one is better okay, but you ask me personally, I will prefer this one But of course, this one much more complicated, right? It got 3 stages. This one in terms of design very simple. Just 1 stage. You can try. You put 12 watt here or 34 watt. Your output you just add a transformer. That step up 10 times. You will still get the same power. But the thing is that you will have a big transformer here. Okay, you will have a big transformer here for the output. All right. So these are the 2 types of design you commonly see, okay, in the commercial inverter. All right, the commercial inverter. And you will notice that, you see, these are the 4 transistors. The 4 transistors, you can see the whole piece of metal here is the heat sink. Okay, these are the full bridge, 1, 2, 3, 4. Okay, 1, 2, 3, 4. Okay, the 4 transistors are here, the 4 transistors. Okay, for the switching. So like I said, you need to know all these 4 in order to create, commercial product. Okay, if you just know this, you can use a transformer method. So these are only stand alone. Remember, stand alone. All right. widely used in bus, camper, car, whatever lah. You know, they put the battery there. They can, you know, operate fridge, whatever electrical appliances use your house. Then you can use it inside the bus. And also, of course, airplane as well, right? Airplane, right? They, you know, they will have this inverter inside, okay, so that they can power up all the AC appliances inside the plane or even ship, okay. So the ship inside also have this type of inverter. Okay, this one you can download and play around. This one I model exactly follow this one. Follow this method. Okay, so this was one of my FYP student work. Okay, so he managed to model exactly the same the commercial, and we test it, the output is same. So you can see that, okay, it has a battery of 48 volt. It goes through a push-pull. See, this is the push-pull, what we call this inverter. Then after the push-pull, right, there is a small transformer. This one, it represents the small yellow one. And then we have a rectifier. Okay, so this blue color is the DC-DC step up. Then after that, we will have the bridge. Okay, we will have the bridge, and then the L and C, and then the output. Okay, so it is proven that, okay, yeah, it is working lah. All right, for that. And then this, if you want to understand more, you can play around with it. And then this student also published a paper. So he explained everything in detail. You go to the MATLAB site. I have put a link so that you can actually read the paper. Okay, let me just find the paper. Okay, he straight away published in a journal. This is a Q2 journal. Okay, back in 2020. So it's a very good paper, you know. And then, okay, you can see this is a model. He explained how this thing works in detail, and even show you how the waveform will look like at every stage. And then the full bridge, okay, and the PI control, what are the value is set, and why is set this value, and then how THD is calculated, and then the tracking stability of the output, okay. And then in order to prove that his model is correct, right? Like I said, I have one of these in my lab. So we actually test this out. We actually set up the whole thing to power the aircon. This is the inverter I showed just now. And then we have a whole battery system to power up a small isolated labs in UCSI. That means this lab is not powered by TMB. It's fully internal, powered by solar and battery. So, and then he calculated the performance efficiency, and then the battery charge discharge. Okay, commercial, and you see it's very accurate in the way that commercial and simulation, of course, sure got a bit different one, right? Okay, but the difference is not that much. Okay, so yeah, so it's a very good. I'm not sure you know this student or not. Chong Bun Chuan. So this is part of it. Okay, so you can yeah, you can download this model, okay, and play around if you want to learn more about this inverter. Okay, now we move on to grid connected. Okay, this is the last part of the single phase already. Now, like I said, they stand alone, right? Will not be worried about the what we call phase, right? Because it's sine wave, right? So the phase must be same. If the phase are different, what happen? It will trip. Okay, the inverter trip or the TMB side trip, either one of them trip. So synchronization is a challenge. And then secondly, you are connected to a grid, right? It's not connected to a load. If you don't control it properly, what will happen? The power will flow in instead of you inject power into the grid, right? Okay, so it will cause problem. Okay, so let's look at the control structure. Now the control structure, okay, first thing very important is PLL. Okay, PLL stand for phase lock loop. Remember, I said grid connected, your phase must be same as the TMB phase. So in order to do that, there is a what we call a system called phase lock loop. So PLL is to make sure that your output, okay, phase is exactly the same as the TMB phase, so you can match. Okay, so that it won't cause any trip. So how do you get the phase lock loop? You get it from the grid voltage, V grid. Okay, so it feedback, okay, to the phase lock loop. So the phase lock loop detect the phase, all right, the phasor. Now it use a phasor to generate a sine wave. So meaning that I have a sine wave here. This sine wave will be exactly the same as the TMB sine wave, right? If the TMB sine wave is like that, let's say 90 degrees, the cosine, here will also show a cosine. Okay, so that's why it follow the grid phase. Then after that, the output of this one will be a sine wave, right? Then it go through a feedback control. This feedback control take the current. Okay, the current of the inverter. How much current the inverter injected to the grid will be coming here. So that means the I reference sign, if I set this one 10 amp, means that I tell the inverter you're going to inject 10 amp into the grid. 10 amp, 230 watt means what? You are injecting 2,300 watt to the grid. Okay, this is how the grid receives power from you. Okay, then of course, like nowadays we have the net metering, then you can earn money lah. You are selling power to the TMB. Okay, of course the source usually is a solar. Then of course this one is the usual PI controller. The PI controller, all right. And then the output of the PI controller here will need to add. Okay, this is the add with the grid voltage, so that the output of this one will be the sine wave. Okay, and then norm. What is norm? Norm is the normalization, because let's say the grid, the peak voltage is 325, right? The peak. So we need to normalize it so that the peak here will be the same, 325. So the normalization, okay, is to divide this by 335, so that you will have a sine wave here that is normalized to 1, right? Plus 1 minus 1. Then the rest is history already lah. SPWM, and then this switch the inverter, and this is how you connect it, okay, to the grid. So you can see the difference is that you see this part same, this part remain the same, right? The principle of DC, AC, these two part same. The only difference is after, I mean, for, okay, it should be this part lah, different, right? For normal off grid, you just need a PI to maintain the voltage. That's all. You don't need to worry about current. But for grid connected, you need the voltage, but you don't need to know the voltage amplitude because the TMB grid, I tell you, I'm 320. So you know, you just need to know, okay, now how much current I want to inject because you are no longer connect to a resistive load, right? The resistive load determine how much current you go in, right? Ohm's law. But now the grid is just like a pool of sea. You know, you can pour a lot of water or little water up to you, as long as the grid can accept. Obviously can, right? 1 megawatt of grid also can. So you need to control how much power you want to actually inject it to the grid. So it is through the feedback control here. You see the feedback. Now these two act as your reference, right? This is your reference. Now for off-grid, the reference is just a block that state your voltage. But now it's grid connected, right? So you cannot state your voltage anymore. You have to use PLL. So this is how, this is a very fundamental one already. I try to choose the most easy to understand. I can't think out of any other that easier than this one. Because when you come to three-phase, more scary. Okay, any questions? It's important you know, you see when you design inverter, right? You need to know two things only. One, topology. When I talk about DC, AC, single phase, you know 4 transistor pump, connect, that is the topology. Second is their control method. Okay, voltage feedback grid connected or not. So you need to know this. Okay, so now let's move on. Look into PLL first. I know you may have no idea how this thing works. Now the good news is that MATLAB have a PLL blocks. So the PLL blocks input is your sine wave, right? Let's say this is your TMB grid lah. I put a sine wave. You basically no need to set anything except this one. You don't need to set your frequency or system. Okay, we are using 50 Hertz. In MATLAB, okay, it is 60 Hertz. You just need to set. The rest you don't touch. Unless you're very familiar with PLL, you want to kacau lah. Okay, otherwise, you know, it's already good enough for you, okay, to do this grid inverter. Now, the output is that you will see, the top one is a sine wave, right? And the bottom one, you look at it like it's a sawtooth. But look carefully, this is radian, right? 0 radian, okay? 90 degree, no, 180 degree is pi, right? So radian here is 3.14, right? It's a pi. And then when you go up to 360 degree on top, right, you can see this is 6.28. So it returns to 0 degree, the radian, in the radian unit, and repeat, radian, repeat, radian, repeat. So that means it tries to find every angle. Like for example, here we know it's 90 degree, right? It's half pi, right? So you go down, you can see it's half pi. Okay, the value is here. Okay, it's half pi. So this is how the phase look work. So no matter when you change this phase, right, you will see this one will move accordingly. So you actually track, okay, the phase of the grid incoming voltage phase. Okay. All right. Now, this is how you implement. Okay. Okay, now you will notice that something very different compared to what we've done previously. Okay. Where is the 4 switch? Missing. Okay, no, it's not missing. You see, previously we are using this, right? Wow, the 4 switch. Okay. So now this is just a simplified method. We are using a block, okay, that can represent the 4 switches already. This is a specialized power system blocks. Okay, so it makes your system much more neat and clean, I would say. The disadvantage is that you cannot model each transistor so detailed, but it's good enough to show you the inverter functionality. Okay, so later I will go into this to tell you, okay, where to get all this stuff. Okay, similarly, okay, well, our input is here, 400 watt. We have a capacitor to hold the energy. This one without is still okay, but practically you will still need a capacitor to temporarily hold the energy. And the output. Now, when you have grid connected inverter, right, we no longer just use L and C. We call LCL. You need another inductor here. Why? Because this inductor represents the grid. You see, this is the power already, right? The grid is no longer connected to a resistive load. So this one, okay, you need it when you have the grid connected, what we call this inverter. And then remember we have this wattage feedback. The wattage feedback, remember the V grid, we take it from the grid. Okay, the V grid come into PLL, right? This is the PLL. Okay, this is the PLL. So it's the same like this one, come into PLL, right? Okay, so the PLL output, okay, it go to the sine function. So it convert the phase to the sine. Now, if you change this to cos, right, your inverter is injecting reactive power instead of active power. So this is how the inverter can control how much active power or reactive power you want to inject to the grid. In other words, nowadays, old inverter does not have this function now, but new inverter, you can literally control the power factor without any capacitor bank. So this is the beauty of power electronics. Okay. And then, okay, now you will notice that, okay, active current, okay, remember I said this one represent the I reference, right? The I reference, you want to inject how many current? You set here, the K setting, 10 amp, 1 amp, 2 amp, 3 amp. Then after that, you come here, feedback from current, okay? You will notice that it's exactly the same, right? Feedback from current, right? The output current. So the current is taken from where? Remember, the current is taken from the inverter side, not the grid side. You take it wrong, I don't know lah. You will get very funny output. Okay, because you want to measure how much the in power. So you take it. That's why you see I put color lah. So you know orange is connect. I no longer use line, you see, because otherwise it was very confusing. So I use the port to tell you this is connect here. Then after that, go through a PI controller. Then after that, remember we need to add or back the voltage. You look at here. Okay, PI controller, and we need to add them together. Then after that, normalization. Okay, normalization, and the rest is history. Okay, the SPWM. Now the same SPWM blocks in the old one, we need to split them out into 4 wire, right, to connect. If you use this block, right, you no need, because internal it connect for you. So you just need this line to connect to this PWM, that it will switch for you. Okay, and then the interesting part is that now, how do I know whether my inverter is working or not, right? So you need to measure the output grid current and the grid voltage. So there is a blocks VI, you can see P is the real power, Q is the reactive power. So you can know, oh, you can actually inject reactive power, okay, and of course because of some phase shift, you will still have a little bit of this reactive power. So this is how the inverter, grid connected inverter works. All right. Okay. Later we'll come back for the simulating. Let's move on the theory side. Okay, now we look at the LCL filter design. Okay. Now the first part is the same as the LC design. First of all, you need to know what is your inverter power rating. Okay, 5 kilowatt, 2 kilowatt, your power rating, right? So you calculate the current, right? We know the power, we know the voltage, we know the current. Then same rules apply. Maximum inductor ripple current is 20%. This one same as your LC filter. The only difference is that it's the three equations that you use to calculate the L1, the inverter side, and L2, the grid side, okay, and then the capacitor C, okay, capital C. All right, so you will notice that there is a S. You will notice that, right, for grid connected, what we call inverter, they no longer use kilowatt. They don't use real power. They use apparent power, kVA, because it consists of active and reactive component. So don't be surprised when you go and buy inverter grid connected. It's 2K, you know how many? 5 kVA. But you buy those off grid, okay, it will tell you how many watt real power. So that is the main difference, okay, between this what we call this off grid, okay, and standalone inverter. All right. Okay. So yeah, this is how you actually can calculate. Okay, 5% design. Okay, with L1, 20% ripple, 5% of rated power. Okay, and then 5% of rated power is here 0.05. Like so I say S is 2 kVA, right? 2 kVA rated power. Okay, and then the L1 plus L2, right? The total at the L2, right, is 10%, which is 0.1. And of course, the first ripple current 20%, okay, is here. All right. Make sure you know where all this number is substitute into the equation correctly in order to get, you know, this. I know like you simply put also work, but cannot like that one, you know, if you do a real design, okay. So yeah, switching frequency is 10 kilohertz. Okay, so I didn't provide any answer. You have to calculate for yourself. All right, for all these the value. So VO is your output voltage. Okay, your VO is output voltage. And remember, okay, 2 by F. This F is your 50 hertz. And the FSW is your 10 kilohertz. These are very common mistakes our students make. They thought a frequency all 10K, 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 then you get something very weird output. All right. So all this equation got red box means what? Damn important, right? So please remember it. Okay, so up to this point, any questions? Okay lah, until you try lah, right? Otherwise, no question. Okay, similarly, you can derive the transfer function of the LCL filter using S domain. All right. So this is how you get after simplifying. All right. You will get this one as a transfer function. And of course, the resonant or cutoff frequency to verify whether your design is correct or not is still the same. Okay, this rule still govern as long as your F naught after you calculate your L1, L2, and C, right? If your L naught is 4 in between this range, you are safe. Okay, so you are safe. Okay, another thing important is that grid inverter LCL is much more important in the sense that it causes safety issue. You see, LC you calculate wrongly, never mind, because the load is isolated, right? The most it explodes your load lah. That's all. Okay, but now you're connected to the grid, you know. If the LCL got problem, it's going to be big problem. If the system if TMV don't trip, the power instead of injecting, it go into your inverter, you cause explosion. Right? So yeah, you always say, Allah, every time I think I put also work one. No, don't do that. Okay. So now let's look at okay, there are many ways, okay, to determine the KP and KI value. All right. So this is only one of the way, okay, but not the best way and not the worst way. Your PI tuning, there are tons way and there is no one standard way for a problem, right? Different plant, right? You have, necklace, method lah, this and that. Even from converter, right? Oh, I tell you, I almost headache lah. So I choose the one simple enough for you to remember, yet it still work. But I say, you come to real design, you need to put more effort on reading it. Okay, because on DC-DC, there is another way of doing it. Okay, now one of the things is that you need to determine the controller time constant. Controller time constant is based on your switching frequency. Okay, then you will get this time constant, 100 microsecond. Then to determine the KP, you use your L1 divided by your time constant. To determine the KI, all right, you use R multiply by the L1 divided by your time constant. All right. Now this R, right, you will see where go R? No R, right? Now, as we know that in the real inductor, there is actually a serial resistor, right? It's wire anyway, it got resistance. But the resistors are so small, usually like 1 milliohm. So people just assume it's 0. But if you assume it's 0, it won't work in this equation, right? 0 multiplied by L1, it becomes 0 divided, then your KI is 0. So you need to assume, I mean, if you have the inductor yourself, you measure it, you put that, you can. If no, you assume it as 1 milliohm, that will do. Okay, you assume it's a very small value. Okay. Then you will use it to calculate the KP and KI. Now, here you will see the output. You will see that, right? The output at this point, after your reference current, it looks something like that. Okay. And then after your PI plus your grid voltage, you can see is almost sine wave already. Okay, and then of course after normalization, then it can be used to modulate the SPWM and then go and switch your, okay, the full bridge. Okay. If everything works fine, all right, this is what you see. This is your voltage. This is your current that is injected into the grid. Okay, let's do some simulating. Okay, yeah, I forget to put the link here. Okay, you all can get the same thing from MATLAB out of chain. I forget to put the link. Sorry. You all know where to find me already, right? Okay, just go to File Exchange. Okay. Okay. I also forgot what I named it already. Well, I should be here. Okay. Oh, not three phase. This is later. Mana. Oh, shit. Maybe I forget to upload also. Okay lah. Grid connected inverter. See got or not? Hey, God. Hey, no, three phase. I upload the wrong one. Wait. Oh my goodness. Okay, I think I didn't upload. I upload the three phase one instead of the single phase. Okay. Then I will upload later in this case. Oh, sometimes too many already. I also do which one and which one I can't really remember. From time to time, I upload. Grid converted. Okay lah. So confirm data. No wonder no link. I just got three phase. Okay. Try again. I think no single phase. If got, it should pop out already. Okay, never mind. So I will show you live here. Okay, so this is the inverter. All right. Now, you may need to know, right, where to find this block. Okay, this block is inside Simscape. Okay, electrical, specialized, okay, power system, and it's under power electronics. All right, so from here, you go to the last one, universal bridge. Okay, this bridge, right? The good thing of this one, it can do all the different converter. Like for example, your thyristor control, you double click, you can choose how many arm. Okay, one arm is half bridge, two arm is full, three arm is three phase. So let's say two arm. Here you can choose the power electronic device. This is thyristor, right? We can choose MOSFET, or we can choose IGBT. Okay, then you can apply. Okay, then you will see this is how it changed. Okay, it changed to the bridge. Now you notice that one side got plus minus, one side got AB. So the plus minus is the DC side, the AB is the AC side, and the G, okay, is the switching control. If you look at the help file, right, it will show you, okay. Okay. Wow. It will show you, okay, is it either diode, thyristor, okay, or transistor, okay, and so forth lah. So this is how you can, you know, change the configuration, okay, of all this. You can see inside the chain, okay, and of course for bridge you just change depend on MOSFET, okay, or IGBT you want to use. So this is a very convenient way for you to test your idea. Okay, and then when you want to really implement the real inverter, then maybe the transistor you buy, right? Then you can do the detail. Okay. Okay, so these are in terms of connection, right? You no need to have all this converter, right? Because it's designed for power system. So we have a grid. Okay, the grid here is 335 50 hertz. All right. So okay, the rest is quite straightforward. Okay, this is the P and I. Okay, the P and I. And then, okay, normalization. Okay, normalization, you are 1 divided by 400. 400 is the DC voltage here. Okay, remember we have the modulation index. Okay, so you have to make sure that, okay, if you change your DC to different voltage, make sure your normalization change. SPWM, very straightforward. Okay, it's 10K. And then, okay, we have a current setting. Okay, we have a current setting. So 4 amps, but it's the what we call this the peak value, right? So it's multiplied by 1.414. Okay. Okay. So now let's say we run. So you will notice that 4M 230. So 900 over what, right? So you can see that the output is 900. Okay, 06. And there are a bit of reactive power here. You see, if it's 100% real power, you will get 960. But there are some reactive power here. That's why you get around 900 watts. Okay, because the system will become much more complex. It takes more time to run, right? I think I run for 10 cycle. Okay, so now from here you can see the output. Okay, very nice sine wave. I think even you zoom in, you won't see much of this. Okay. See, very, very smooth. Not even a, zigzag thing. So, okay, I didn't measure the THD. I believe it is very low. Okay. And we have these power measurement blocks. You just make sure it's set to 50 Hertz. And these blocks, you can find in the measurement sensor and measurement somewhere here. Okay, the power. Okay, to help you to measure the power. So, for example, if I set this to a higher current, okay, let's say I set to 8. You can see the power now go up to 1,102, right? Because I increase the current. You see this grid connected, right? The power is determined by how much current you injected to the grid, because voltage is fixed. Voltage is fixed, okay? So you inject, like this case, I inject 8 amp, so I got around 1,800. So this is how the grid connected inverter determine how much power you want to use internally for the house and how much power they want to inject it, okay, to the grid. So it depends on usage. If the price is good, right, then you inject everything, okay, then you earn the money, okay. So there are many countries have this what we call feed-in tariff net metering scheme, where you can sell power to the TMB. Now let's say if okay, let's put it back to 4 first. And I change this to cost. Okay. Now you can see I have a lagging power, negative 800 something. And my real power is only 74 watt. Of course, TMB you cannot sell reactive power to TMB. TMB they will put a meter there that's only read real power. If you set it wrongly, you inject reactive power, TMB won't pay for your 800 watt. It pay only for you for your 73 watts. Okay. So this is a lagging. Okay. So now you look at the waveform. You will see it is out of phase 90 degree, right? The current and voltage, because you are sending reactive power. So in other words, reactive power you want to send. Okay, it's a very important features for this what we call this microgrid. Okay, so you can control because this one means a very high power factor. Okay, means very high power factor. Okay, so nowadays all the new inverter in the market have this capability to control real power or reactive power, okay, to be injected to the grid. Okay, so up to this point, any questions? Wow, no question. Okay, maybe we do a little bit of simple exercise. I think the rest is quite straightforward, right? Inductor, all this. Something new today is the PLL, right? Let's do a PLL, okay? I think this should be simple enough for you all to do it, okay? Where is the PLL? Okay, we try to do this one. Okay, so I will do it as well, so you see how I do it. Okay, of course, I have to open a new, okay, a new Simulink, and then I need to find PLL. Oh, I also don't know where the PLL is. It should be under the control. Under control. Okay. Control. Okay. Under Simscape, electrical, specialized, control. And there are two PLL. One is 3-phase, one is single phase. And like I say, if you are using a 3-phase inverter, you use a 3-phase PLL. So we take this PLL, okay, over here. And then we need to have a sine wave, right, as an input. So we take the sine wave as a source. Sine wave, okay. And then we need to have a scope to see how this PLL track. Okay, so we need to have two input. One, two. Okay, we have two input. And then the output is omega t. Okay. And of course, this one is to be connected to this. And then the time 0.1 second, 5 cycle. Okay, inside the PLL, like I said, because the PLL have a PID controller, unless you know what you're doing, or else just leave it there. Let's touch this one. Okay, 50 Hertz. Of course, the frequency is to tell you what is the frequency, so we can eventually put a display. Okay, to actually read the frequency if you want. Okay, I just put here. All right. So if everything is okay, not yet. Frequency here, okay, 50 Hertz, right? 2, 5, 50. Okay. So, all right, should be able to run. Let's try. Okay, the PLL will tell you the frequency, and then it will show you this. So if I change this sine wave, right? Now it starts from 0 degree, right? So the PLL will start with 0. Now, what if I start with 90 degree, which is pi, okay? Phase in radian, which is pi. Or you can type 3.14 also can. Eh? Oh, half pi, sorry. Because it still starts from 0, right? 90 degrees, sorry. Okay, pi divided by 2. Okay. Okay. Now, you will notice that, right? It still starts from 0. And you can see here is a bit, because the PLL is trying to track. It does not track immediately. Remember, inside got PI controller. It takes time to track. Okay. So you can see here, it will try to adjust itself until, okay, this one becomes shorter, this one longer, until somewhere here, okay, it almost track to the 2 pi already. Okay, almost track to the 2 pi already. If you want to see a longer one, then you just add the time. Okay, so this will happen because when I look at here, I know already it's supposed to give me 50 Hertz, right? But now only 49.86 is still not fully tracked, but very close already, very close already. Okay, now when we start from 0, everything is perfect, of course. You don't need to track, it's already there. So when you change, right, for example, let's say I just put a longer time. Okay, now you can see it's 49.91 already. Okay, so you can see they are still slightly, if you zoom in, you will see you see, something like that. You try to track. So like I said, if you're good enough in the PI controller, you can change this true value, KP, KI, KD, so that it will track faster. Okay, it will track faster. You see, it also gave you a time constant. So this one is basically based on the equation I show you. The divided by the time constant. There is an equation for this. Okay, so that is the idea. So yeah, another 10 minutes. Okay, so please do this. So if everything is okay, right, you should be able, I mean, we still run at 0.1. Okay. Okay, so now you see the output of this in this inverter, right? You can see the output of this I put into this sine or cos function. So it would generate back exactly what is input. Okay, this is how it works. Okay, I go to I go to maths operator. The maths operator, we have this trigo function. Where is my trigo function? Trigonometry function. Okay. Okay. So now after I get a sine wave, so I run again. Okay, you can see it tried, this is the input, the grid voltage. This is the output. You see, it's trying to track the same. Here, like I said, because the phase different, you see, it starts from 90 degree, but your PIL starts from 0. So the PID control, what here you can see, it try to adjust until it slowly matches it. This is how the PL, like I say, if I want to send reactive power, I change this to cosine. Okay, I change this to cosine, so the output is cosine. Okay. Okay, so the rest, multiply by how much is the amplitude of the current. Is everything about the control feedback already, right? And then PI and then so forth. This is how things works. So I believe this is something new for you guys. So yeah, it's also important because when you come to real hardware implementation, right, this part is important, okay? But it can be easily programmed using Arduino. Easily programmed. Okay, so come, let's do it. And yeah. Or maybe you want to make it look nice, you just make it 0 lah, okay? You make it 0, then it look nice, okay, 50 Hertz. See, the sine wave in, sine wave out. Wow, today is super fast. Wow, 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 wow. On the flip side. Oh. Yeah, wait should be because yeah, I should update it, upload it later. Okay, because I think I still have another one I need to upload for you all to understand how three-phase inverter work. If I don't upload that one, you all will be like in haywire. Because I don't expect you all to do three-phase on the class already. It's very much complicated. So also in view of time it's already week 7, we are still stuck here. Cannot. 3 more type of converter, we need to move on already. Okay, phase lock look good. I think no challenge at all this one. Okay. Because this is a very common question, they don't understand. How do you synchronize the phase with the grid? Okay, and then I hope this PLL part explain everything, and also it make people confused. How can you control real power or reactive power to be injected to the grid? It's also because of this PLL and the sine cos. That's all, and the rest is history. Oh, cool. Wow. This is a very good example to show how you can make use of your phase angle to generate sine wave or cosine, okay, for your inverter references. Because our inverter, right? Remember when we talk about SPWM, okay, the sine wave is the reference, okay, and then how much of switching frequency determine the resolution of your sine wave, that indirectly determine the total harmonic distortion. Okay, so I'm grateful that you all participate in this simple PLL exercise. All right. Okay, any more question before we end the class today? I think today, let me see. I think we just wrap off the single phase. Okay, so like I said, yeah, the most complicated part is the phase lock loop. Okay, I believe this part, if you can understand what we done, this will become the I reference. Remember, the I reference, okay, for your feedback control, and the rest is history. Okay, normalization, add back, and then this is the SPWM. Okay, equation again. Okay, so grid connected application is basically, okay, for the solar PV or wind power, what we call inverters. So how it works is very simple. The input is your solar panel, and it will go through one DC-DC converter first, which we are going to talk about it after the DC-AC. And then it will go through our full bridge DC-AC. And then of course we connected to the TMP grid. Okay, so this is actually a very simple device. When you open up, wow, they charge you like how many thousand? You look at it, wow, like I said, they are not only selling you the product, they are selling you the knowledge of creating those products. Okay, so knowledge is expensive, right? Because they are selling a lot of things. You look at it, if you make it yourself, it's not that. Why is expensive? So okay, so yeah, these are the single phase inverter. Another application is the Tesla Powerwall. Okay, so it's the same. The battery is here. They have a DC-DC converter. Okay, and the DC-AC that connect to the grid. And you can control how much you want to inject to the grid, how much you want to use for your house. That is the beauty of this. When this thing comes, people say, wow, so good you can control. Bullshit lah. You know the theory is okay. It's PLL, right? And then, of course, if you are battery, here is PV. PV is unidirectional, means the power will deliver from here to here, one direction. But for Tesla power, it's bidirectional. See, bidirectional means that the power can go in, go out, at the same time can go in to charge the battery. So it's bidirectional. Okay. So bidirectional, is it something very hard? Actually, no. What we are doing, right, is actually a simple bidirectional already. You see, if you look carefully, look back at this circuit. Okay, 4 transistor, right? When you switch, power will take from here, go out, right? But if I want to charge the battery, what should I do? I just put 0, 0, 0, 0 here, right? And you see this 4 diode? It form what? You look carefully, it's actually forming a bridge rectifier. Remember, I already turned off the transistor. You look at this 4, 1, 2, 3, 4, right? Now the transistor is disappear because I turned off. The transistor is disappear. The transistor is disappear. The transistor is disappear. It's off my isolated. So my AC come in. And then of course, you need to have a capacitor to do the filter lah, right? That's why the capacitor has to be there. So when you turn off all this, send all 0 to this one, your inverter become a rectifier and if power go in, will start to charge your battery. As simple as that. And they sell you how many thousand USD? You know? Okay? But I don't cover much on this lah, because we just I'm not sure we got time or not lah. Because the course online is about one direction, but I just take the opportunity to tell you, it actually can be, you know, you turn off, it becomes a rectifier. Okay. Okay. Okay, what else? Okay, we have off-grid, we have PLL, okay, we have LCL design, we have feedback, application, Tesla wall, power wall, all done. Okay, next class, we move to 3-phase already. Okay, so, wow, how many slides? I'm very worried about 3-phase. Slide, almost there already, 91. Wow, 134. Okay lah. Okay. Yeah. Any questions? Because after 3-phase, we are done. Okay. Okay, move on already. Okay. So if no question, okay, we will end the class today. All right. Thank you.